Okay, so welcome everyone. Hope you had a nice weekend. And today we're going to be talking about time travel. So, 14th of March 2018, Stephen Hawking had a party for time travelers at Cambridge. So, what he did was that he sent out the invitations to the party after the party had occurred. No one but him turned up, but it's not to say that he's not a time traveler. But does this absence of time travelers show anything about their possibility? So, going to ask basically whether time travel is physically possible according to laws of physics, and is it metaphysically possible? Is it not prohibited by some reason? So we'll start briefly by saying, well, what is time travel? We'll then look at time travel in physics, so whether it's permitted according to our theories of general relativity and quantum mechanics. And then we'll look at some of the metaphysical paradoxes that seem to arise if time travel is possible, and do these paradoxes mean that perhaps time travel isn't possible? Something like this. Okay, so what is time travel? Taking the definition from David Lewis, who was quite pioneering in writing about the metaphysics of time travel, he says that an object time travels if the difference between its departure and arrival times, as measured in the surrounding world, does not equal the duration of the journey undergone by the object. So, in doing this, we need to distinguish two different sorts of times. Firstly, there's the personal time of the time traveler. So this might be measured, for instance, by their wristwatch, or by their biological aging processes, the accumulation of memories. This all goes in, one sort of direction and at one sort of rate, is the idea. And the external time will be the time of the rest of the world. So time travel is kind of a discrepancy between these two times. If the time traveler hops in their time machine, travels for 1 hour, and then gets out, when they get out, 1 hour won't have elapsed in the external world according to the external time. It might be before or later. So this definition also applies to the idea, I read that it was in some movie, but I can't remember what it was, where the person gets in their little time travel box, and to go backwards in time, say for 1 hour, you have to sit in the box for 1 hour. So in that case, it would be like a negative hour, even though it has been an hour that's elapsed in the world, it's gone the other direction. So minusing the departure and arrival times, in that case, you get negative hour. Okay. So today, now turning to the physics of it, we're going to just be working with some main assumptions. Firstly, I will be using the block universe conception of time because it's supported by general relativity. So to remind you, this conception of time holds that all times exist. So the past, present, and future, they're not objective distinctions, everything's out there, timelessly existing, laid out in sort of a block. So treating time as we do space. And, sorry, in this picture we'll also be assuming, as we've seen, that there's sort of an emergent thermodynamic arrow of entropy due to some very special initial conditions in the universe, and that our personal arrows of time tend to align with this. And similarly, we define cosmological time as the kind of increasing in the direction of the expanding universe. So these are just the assumptions we're going to be working with. We've discussed them already in previous weeks.
Could you just, do you not include in the definition when you travel nearing the speed of light, so that the time goes slower for you traveling, that would be also captured by the definition, wouldn't it?
Yeah, that would make a discrepancy, between your personal time and external time. Good. If you're moving very fast with respect to something else by which you're using to define the external time. Yeah. Good. But that might not be the only way to do time travel, but it's definitely one way. So what does general relativity say about time travel? Well, firstly, what is general relativity? It's our current best theory of space-time, and it defines gravity as the curvature of space-time due to the presence of massive objects. So here it's supposed to be a depiction of the curvature of space-time around the Earth, because the Earth is very massive, of course. And this curvature creates the effect of gravity. So this satellite will feel the curvature of space-time as gravity, and that's what keeps it in orbit around the Earth. So in a slogan, due to John Wheeler, this isn't due to Einstein, it's a later physicist who's interpreted what this theory says that matter tells space-time how to curve, so the Earth's told this space-time how to curve here, and in turn, space-time tells matter how to move, so it's telling, for instance, the satellite how to move around. So it's a non-linear theory, it feeds back on each other in a way. Okay. So what's time like in general relativity? Well, as we've seen, it uses this block universe view, so there's no privileged time slicing. There's no single objective now that obtains everywhere in the universe. There'll be different times depending on your state of motion, as we've seen in the case of special relativity. And if you're moving very fast with respect to another, time will slow down according to your wristwatch, your personal time. Also, it says that time depends on your state of motion, and it also depends on the strength of the gravitational field or the space-time curvature that you find yourself in. So time will actually be slower for an object in a stronger gravitational field. So these two effects, they've been very well tested. The theory's been very well tested. And what you'll hear is that actually, using the GPS on your phone, it has to send signals up to the satellite up there with the who's doing the GPS clocks. And the clocks up here, they're in a weaker gravity because it's very further from the Earth than us sitting on the Earth. And also, it's moving fast. So together, actually, the satellite clocks run faster than ours, I think that's how it works. And by a rate of like 38 microseconds or something per day. So in developing the GPS technology, you have to take this into account, and that's what they've done, and that's why it works. So these are two ways in which GR apparently allows time travel to the future. Firstly, by going really fast, and secondly, by sitting in a really strong gravitational field. You can kind of sit there for, say, 5 years, and then you come back to Earth, which is in the weaker gravitational field. And you'll see that the external time on Earth, a long time has passed, and a shorter time has passed for you. So it allows time travel to the future in this way. The strong gravity might be provided, for instance, by black hole. There are rotational black holes, curved black holes, and Hawking thought, well, if you sit kind of at the right place in there, you might not get sucked in, but you still also have to be accelerating around very fast. Another kind of hypothetical view is this idea of cosmic strings, which are hypothetical objects with very high gravitational pull. The idea is that if you go near them and take a sort of a trip, you could also time travel to the future. So we've got time travel to the future. What about time travel to the past? And here there are two sort of options. Firstly, there's this idea of faster than light particles. So again, quite hypothetical, they're known as tachyons. So you might think, well, isn't that already prohibited by special and general relativity? It's actually not. As long as these particles were like always going faster than light and never started off kind of lower than the speed of light and sped up, so they had to be accelerated, then it's actually not prohibited by the law. But I'm not really going to be discussing that. The other possibility is this idea of closed time-like curves. So, well, sort of the same thing. If you go really, really fast, you can have causality flipped around is the idea. But, sorry, that was for that one. But you remember the light cone structure of special relativity, which depicts your causal structure of space-time thanks to the finite speed of light. Hopefully you remember this. So the idea is that if this is you're an event located here in 2 dimensions of space and 1 dimension of time, then everything located in this region of space-time you're able to influence, because these lines here mark the light cone that can emanate from you. Every signal you send out, if it's going the speed of light, it will go on these cones. And anything that you send out slower than the speed of light will be within this. So that's your causal future. And similarly, in this domain, region of space-time is everything that could possibly affect you when you're at this point of space-time. So it's everything that has signals at or slower than the speed of light. Yeah.
What's the reason for the past light cone that you can't influence it in normal circumstances?
So in this, again, it would be requiring that you send out a signal kind of faster than the speed of light. So it would have to be on this side, and then it would have to go way, way faster to get all the way down there.
Why? Because it looks symmetrical?
Mm-hmm.
So I don't understand why it's harder to get it down there than up.
Yeah, it's just defined by having the speed of light here. So anything in this region out here can't influence you and you can't influence it. But these guys, if they send out a signal, they can reach you. But yeah, you can't, for you to send out a signal there, it would have to be something like a tachyon that's going faster than the speed of light and traveling therefore backwards in time.
Is that because of initial conditions, or is that?
No, it's due to the structure of the space-time itself.
Okay, so
yeah.
that's compatible with the block universe?
Yes.
Okay.
Yes. So, for instance, this is a particle trajectory. Say it's moving through space and it's moving through time. If you were just sitting at one point in space, you'd just be moving along straight in time, moving upwards. So, yeah.
But if you were to travel faster than the speed of light, wouldn't just the cone be kind of wider? Or is it theoretically possible to go so fast that the cone curves back into itself? Is that kind of the idea?
You'd need a different structure space-time, so we'll come to some of these, yeah. So there are some solutions to Einstein's equations of general relativity that allow for space-times in which you have a world line which could form a closed time-like curve. So kind of what you're saying. Here, the idea of you're moving through space-time like this. So this is always your forward cone. You're going forward, still, forward, still, forward, still, forward, still. And then somehow you've reached back and you're meeting your old past self. Sorry, your younger past self. So yeah, thanks to these structures, space-times, the cones can just totally flip around. So yeah, an object that's traveling in a space-time like this would eventually arrive back in the same position of space-time where it started. This is meant to be just a normal one, and this is the closed time-like curve. So again, it's due to the particular structure of the space-time. So some of how these space-times might look, an instance is this toilet paper tube space-time. So it's the cylindrical roll, and here time is up and space and is just a two-dimensional plane that you've rolled up. And if you're moving in this space-time, kind of imagine going around and around the cone. So forward in time would be moving up around the cone. And then this curve here would be a possible trajectory along such a space-time, which is a closed loop. And in that case, yeah, you can imagine that's what we saw on the last slide of the light cones flipping around at some point and then moving back to yourself. Yeah?
Have we confirmed that it is at all possible that space-time can behave like this, or just something I actually just thought about?
So, yeah, it's a solution to the equation. So it's possible that there's a universe with a space-time like this. I think this one's been ruled out for whatever reasons. But yeah, we don't know the exact structure of our space-time. Well, we determine it experimentally. So yeah, it's possible that it's like this, but at the same time, it's probably not possible that we actually live in this universe. Well, already this one's ruled out because it's got too few dimensions of space, for instance. Another example, which is also a solution to the equations, has this Van Stockholm dust. So it's this kind of rotating tube of dust that generates a really big gravitational field, and light cones that are close to it would again get flipped around, and you'd end up with a closed time-like curve here. In these ones, causality would be preserved because you're going up in time. These ones, no. Okay. And then there's another one, the Gödel space-time, which was shown to be a solution of Einstein's equations by the famous logician Kurt Gödel. I put it in as the readings, his paper, but I put it in for the wrong week. But you can certainly read this paper too, and it explains that we can have time travel in this model. So yeah, it gets pretty crazy, as you can see. Okay, so thanks to just the structure of space-time, it could be that you end up on a trajectory where you go back and time travel to the past. Another possibility, I think with this one though, you couldn't just be floating through space and end up meeting back to yourself. You'd have to be accelerating in that model. But another possibility that could generate these closed time-like curves is the idea of a wormhole. So you have two regions of extreme space-time curvature and able to get them to stabilize and join up to one another. Then you could have kind of this special path, shortcut through space-time. Instead of having to travel from here to here along this route, you could just jump down and end up there. Though in this picture it looks like it's the longer route. Depiction like this, you can see that it could be a shorter route. So these are the same pictures, just different depiction. So this is kind of a shortcut through space, but the idea is that again, very, very hypothetically and speculatively, that if you were to take one of these wormholes on a very high-speed journey and bring back to where it was, time would have slowed down for that end of the wormhole compared to the other end of the wormhole. And then if you jump through, you'll be able to go to the past. So those are your options for time travel in general relativity. Now, look, yeah.
What about traveling outwards from a black hole?
Outwards from a black hole?
Yeah, you're traveling, theoretically, if you're traveling backwards in time.
Yeah. That would be another space-time structure where you're going to do flip. Yeah. Good. So, any more questions about space-time and general relativity? We'll be coming back to it in one of the last lectures. Yeah.
Yeah, I just didn't get how, if the structure of the space-time thing is very clear on the direction of causality.
At any point.
At any point. Yeah. But it's not directly relevant to time travel. But when we had the asymmetry in time chapter, we talked about all this. How can we account for the asymmetry of causality in the B universe? And it seems like there's no problem really if the structure just is that way. Or what do you think?
In this sort of space-time.
Like why we have memory of the past, not of the future, if it's empirically tested.
Yeah, I think that has more to do with the idea of cause and effect, which isn't, is that more problematic idea we were discussing, which isn't taken into account by the laws. All this tells you is that, do it like that, to preserve the causal structure of the space-time, all causality means in this picture is that one event can influence the other or send a light signal. So it does have a sort of direction that says, according to the light cone.
But didn't we say then that the physical law says that if one thing is necessary for a later event, then the later event is also sufficient for the. But that doesn't mean that it can influence it.
Yeah, it doesn't mean it can influence it. I think it means if the later event occurred, then it's sufficient to say that the earlier event also occurred.
Okay. Yeah.
Yeah. Because remember in this picture too, the block universe, everything is already there.
Yeah.
It's not like something's happening. Yeah.
Yeah.
Okay. You ready for quantum mechanics? So, a very brief introduction, because I found some of the stuff he was doing in the book kind of required a lot more background knowledge that he didn't explain. So I'm doing more basic than what he gets to in the book. Basically, what you need to know is that it's a very, very good theory. It's a very real theory. It works. It was developed at the turn of the 20th century. Originally by Max Planck, Einstein, Born, Schrödinger, Bohr, Heisenberg, and many, many others. And it's supposed to describe all matter, all radiation, and as we've seen, we hope also that it's supposed to describe space-time itself, although we haven't been successful in formulating that theory yet. But typically, we only need to use it for describing very tiny things. So even though it technically applies to everything, in practice we only need to use it for tiny things. So what it says is that matter and radiation, energy, it's quantized, which means it's not just a continuum. You can't have a continuous values for energy, but what you have instead are little discrete packets or particles known as quanta. So, yeah, as I said, it works. It's led, so you view it as a framework, and then you can use it to formulate specific quantum theories. And some of these theories, including our standard model quantum field theories, have led to some of the most accurate and well-tested predictions in all of science ever. The problem, though, is that it's not clear how these theories relate to the world. So there's many different interpretations of quantum mechanics that tries to make sense of how the theory actually relates to the world. And yeah, basically, I'm not sure there's any experiments that could tell the difference between the interpretations, but plausibly there could be. I think one interpretation has tried to make some predictions. But other than that, it's kind of open which interpretation you want to choose for philosophical reasons. All right, so you'll hopefully remember back to classical mechanics, where we said that a complete state of any system at a given time t is specified by the position and velocity of all your particles, or all your billiard balls. And once you have the position and velocity of all your particles, you can feed it into your dynamical laws and use this to find the state of the system, so its positions and velocities at any later time or any earlier time. Now, what quantum mechanics differs from classical mechanics quite radically because the complete state of a system at a given time is not going to include a definite value of a particle's position and velocity. And also, or perhaps consequently, is that even though we have deterministic equation, dynamical equation in quantum theory, we can only actually use it to calculate the probability that we will find the system in a particular state at a given time. So there's already something in tension here that I hope you can see, is that how the hell does a deterministic equation only allow us to compute probabilities? Okay. So this comes back to the Heisenberg uncertainty relation, which you should have encountered if you took the exfil in the past few years, because there was a reading by Heisenberg in it. So the uncertainty relation says that this is your uncertainty in position, this is your uncertainty in the particle's momentum. So momentum is its mass times velocity. So to simplify, you can just think of this as the uncertainty in its velocity. And what it says is that this can never be zero. It always has to be greater than or equal to some constant. So, what's uncertainty? Uncertainty is any measurement you take will always have kind of a range of values that the actual value could be in. So if you're measuring position, for instance, you take your ruler, but say you've got like a pretty shitty ruler that's only got centimeters markings on it and doesn't have millimeters. So you line it up and you see that your particle's at 4 centimeters. But then you think, well, it could actually be at like 3.8, or it could actually be at 4.2. It could be anywhere in that range. So then you've got an uncertainty of about 4 millimeters, say. So that would be your uncertainty in your position measurement. If you got like an even better ruler that did have smaller markings on it, then you could get a measurement with a smaller uncertainty in your position. What this says is that you can't have a position measurement that's arbitrarily highly accurate. So the more accurately you know the position, the more uncertainty there's going to be in your velocity measurement. because if there was no uncertainty in your position measurement, if you knew exactly where the particle was, and you knew exactly where what its velocity was, then this would be 0. You'd have no uncertainty. But what this says is that it can't be 0. It always has to be greater than or equal to this number. So the more accurately you know this one, the less accurately you're going to know that one. Alright, and the way I've just framed it is in terms of measurement and how you're going to detect it. So you might think, alright, fine. So I go out and I measure my particle's velocity and I know it to some, pretty good precision. Not much uncertainty in my velocity. So for all I know, there's quite a wide range of positions where my particle could be. For all I know, the particle could be over here, it could be over here, or it could be anywhere in between. Alright, that's pretty weird, but so what? But it's not what it says. It says something kind of much more profound. It's not about our ignorance. If you're imagining that the particle's out there somewhere in this range, it would mean that if you knew a bit more, you'd know where the particle was exactly. But what this says is that the reason why you don't know the exact position of the particle is just because it doesn't have an exact position. The reason why you don't know anymore is because there's nothing more to know. This is the complete description of the particle. So it would say, if you've got a fairly accurate detection of your velocity or its momentum, then the particle is completely delocalized. It's spread out in this range of space. So it says that we can't simultaneously know both the position and momentum of a particle to arbitrarily high degree of accuracy. And this principle is really inherent to quantum mechanics. So Heisenberg says that the complete knowledge of the system must be essential part of, so it's incomplete compared to the classical picture. It's complete in itself. So this means that the laws of quantum physics are inherently probabilistic. It's not due to our ignorance or our measurement capabilities. Okay. So, as I said, if you kind of have more or less precise knowledge of particles' momentum, then it doesn't have a definite position. It's behaving like a wave spread out in space. So it's delocalized. So quantum mechanics describes this wave-particle duality. In some cases, we use this picture of a particle, and sometimes we have to describe the system as a wave. And this is most apparent in this experiment called the double slit experiment. So basically you send out your electrons and they can pass through a sheet of paper with 2 slits in it. And what you see is this pattern at the back, which shows you that the particle's acting like a wave, because this is the sort of pattern you get when waves interfere. So you can see, imagine this like a water wave. These are the crests. So looking at the system from the top, the wave goes through both slits and then it interferes with itself. There's some points where the 2 crests meet and you'll get a maximum, and there's some points where they cancel each other out and you get a minimum. So you end up with this interference pattern when it's behaving like a wave. So yeah, that's pretty weird. You send out an electron and it's acting like a wave. You get this interference pattern. It gets weirder because then you think, well, all right, how could this? You can't understand that in terms of the particle picture, having a particle go through both slits. So you think, well, all right, I'm going to find out which slit did it actually go through. and you set up like a little camera here on one of the slits. And the thing is, once you do that and you find out actually that the particle doesn't go through both slits, it goes through one slit or the other slit. So you don't end up getting this interference pattern anymore, you just get a dot where the particles landed through. So this is known as wave function collapse. So if you make the measurement and find out where your particle's located, it's a particle. So this says idea of complementarity due to Bohr, that the wave nature and the particle nature of your quantum system always has to be kept separate. So it's pretty, this idea of collapse is pretty conceptually unsatisfying, because it's almost like, it started off and it's acting like a wave going through, and then it hits this point where it's being measured, and it's like, oh shit, I better be a particle now. It has to instantaneously go into one spot, you know? So it's this causes quite a lot of problems because it does seem to imply kind of faster than light action. Especially like, what if your camera was at one of the slits and the particle is, found to be going through the other slit? Then it's kind of knowing already what you're doing in a way. So another solution to try and understand this is this idea of backward causation. The electron, it knows if you've set up a detector here when it comes out. It knows, you've got a detector up there, so I'll just be a particle and go through one slit. The reason why it knows is because your future act of measuring it causes it back here to decide in advance whether it's going to be a wave or a particle. So the future act of measurement, when it gets to this point, causes the electron to behave as a particle when it comes out of the ray gun. And in that case, it goes through one slit or the other. So this is one interpretation of the craziness of that experiment. The other interpretation, well, that's it. There's a lot of interpretations. Another one is this just collapse, which isn't so satisfying. So this is this idea of retrocausality. Another solution to this picture is the many worlds interpretation, which says, well, there just isn't a collapse here, whether it's instantaneous or due to backwards causation. In fact, the electron always goes through both slits, even when you've measured it and found out that it's only gone through one slit. So it's like, what does this mean? Everett, when he proposed it, he didn't explain what this meant. It's later people who have tried to interpret it realize that if you hold this view, you're led to this idea of many worlds. So you're also part of the quantum system then, and basically the world splits in two, and there's one branch in which you've measured the particle going through slit A, and there's another branch in which you've measured the particle going through slit B. So could this lead then to a form of time travel where we can change the past and end up on a different timeline? Like, could I go back and then repeat the experiment and end up as the other version of me? Or you might think, if branching is happening all the time, there's so many branches, there must be all crazy stuff going on in all these different branches. Could I go back in time and end up on a branch where my pet cat is still alive after her horrific quantum accident in 2002? So it's very tempting to play around with this because it's cool contrasting to the typical block view. Though this is still a block universe view, it's just all the branches are in the block. It seems like you could change the past. Most proponents of this view emphasize, though, that these branches are actually supposed to be independent and can't influence one another, and you can't travel between them. They say that it doesn't allow for time travel. But there's some proponents that say, yeah, there are some interpretations, which isn't the standard one, where you could possibly have time travel. So again, it's quite open. Okay, so very quickly, this doesn't have to do with time travel, but in case you've heard of this and didn't know what it was, it leads to this, well, another picture is this Schrodinger's cat paradox. Schrodinger, like Einstein, thought this theory just doesn't make any sense, so tries to come up with paradoxes, logical paradoxes that show that there's no way this theory could be consistent. And what Schrodinger imagined, this thought experiment where you have the cat in a box and you've got some radioactive material, all you know is that after some given time, because the radioactive decay is a quantum process, after some time it's either decayed with some probability or it hasn't decayed. And if it decays, then it breaks this poison jar. If it doesn't decay, then it doesn't break the poison jar. So after a certain amount of time, your cat is actually in a quantum position of two states. The state of being alive and the state of being dead. And according to the Copenhagen interpretation, which is one developed by Heisenberg, until you look in the box, the cat, it's in this superposition state of being both alive and dead. On that interpretation, once you open the box, you get collapse again, and the cat becomes either alive or dead instantaneously due to your looking at it. But until you look at it, you can't say anything more than that. On the many worlds interpretation, again, when you open the box, you find the cat either alive or dead. The universe is already branched, and there's a world in which you're viewing a live cat, and there's a world in which you're viewing a dead cat. Okay, so I didn't get to even the paradoxes of time travel, but hopefully we'll do that in the discussion anyway. Is that all right? Otherwise, I'll just quickly go through it. But yes?
You can quickly go through it.
All right. I can quickly go through it. That was the complicated bit. So the paradoxes, again, are now the metaphysical sort, supposed to reveal the logical inconsistency of time travel. So even if it's technically allowed by physical laws, if it leads to some horrible paradoxes, then these may show that time travel is logically not possible. Grandfather paradox says, very quickly, you build a time machine, you travel back in time, meet your grandfather before he's given birth to your mother, you kill him, and then you're not born, and your time machine isn't built. So what does this mean? You both can and can't kill your grandfather. How is this possible? So the solution, of course, according to the block universe, says, well, there's no paradox where you both can and can't kill your grandfather. It just says you can't kill your grandfather before you're born, because the block universe view, the past is already existing and you can't change it. If you were back in the past, which is possible in the view, then it was always the case and is always the case and is timelessly the case that you're always there back in the past in 1952, holding a gun, watching your grandfather, and you didn't kill him. If you did kill him, then you wouldn't be here, basically, to kill him. So it's already known that you didn't kill him. And then Lewis and in Dayton in the the book says, well, what do you mean I can't kill my grandfather? I got the best gun, I practice shooting, I'm fearless, determined, I can kill him. Lewis says, well, yeah, according to one set of facts, you can in some sense of the word, and that, you know, all these facts hold. But according to a more complete set of facts, which includes the fact that you actually didn't kill him, means that you can't kill him because you didn't, because you're here at this point in time. You say, that doesn't make any sense, nothing can stop me, what's going to stop me? And the answer is, well, something stopped you. So we can ask, yeah, is this kind of picture conceptually satisfying and does it make any sense? And just to finish, the other type of paradox is this idea of closed causal loops. So that was one of them, supposedly, except it couldn't happen. Situations where information or objects are of inexplicable origin. So instead of going back in time and killing your grandfather, is it possible, I'm sorry for this, that you go back in time and become your own grandfather? Is that possible? That would be an example of this sort of closed causal loop. There seems to be kind of nothing preventing this, you know. Similarly, you meet an old person who tells you how to build a time machine. You build the machine, enjoy traveling around, and then one day when you're old, use it to go back in time and tell your younger self how to build the machine. So in these sorts of situations, yeah, are they possible or are they not? In this one, you might think, well, there's some sort of aspect of your DNA that's going to prevent this, right? But this one is maybe not so clear. So, okay, that's it. Thank you.